do a quick video on how to prove the sum and difference cosine and sine formulas, or should I say identities. So in the textbook I've seen, the proof for it is it's okay. It's purely analytical, but I find it a bit more difficult to see, uh, mostly because it involves a lot of algebra, because we're constructing points and using the difference to find the hypotenuse. Um, so I thought that I would I thought I would show a different proof, and the proof is quite simple. You just need to know how to set it up. So first, what you do is you create some triangle, and the only constraint for this triangle is it has to have some angle and be a right degree angle. And then on top of this triangle, we construct another right angle triangle. And this has a further constraint. So this has to be some angle beta with a hypotenuse of length 1. And then from here, you could construct a rectangle, or you sort of have to construct a rectangle for this geometric proof. So we're kind of doing what the Greeks did a long time ago. We're doing geometry. So from here, we could first need to recall what the sine of some angle is. So if we have some triangle with an arbitrary hypotenuse, considering theta, our base would be our adjacent and our height would be our opposite length. So the sine of theta is defined as the opposite over the hypotenuse. So we can then argue that the opposite is equal to the hypotenuse times sine of our angle, and then cosine of some angle would be the adjacent over the hypotenuse. So the adjacent angle, or the adjacent side of some angle, would be the hypotenuse multiplied by cosine of that angle. And first, considering the triangle with interior angle beta and hypotenuse 1, our adjacent side would be just the cosine of theta, because our hypotenuse is 1. And it wouldn't be theta, it would be beta. And then for our height, the opposite side would be the hypotenuse times sine of beta, or just 1 times sine of beta. And then from here, we could consider the triangle, which now we know has a length of cosine beta as the hypotenuse. So the adjacent to alpha would now be the hypotenuse, which is cosine of beta, multiplied by the cosine of alpha. And then the opposite side is going to be the hypotenuse, which is cosine of beta, multiplied by the sine of alpha. And then we need to do a little bit more geometry. So first, we constructed these to be right angles. I should have drawn them earlier. So firstly, the easier angle to prove is this one right here, being alpha plus beta. This is because we have alternate interior angles, right? So if you have some line and some intersecting angle, the other. These would be congruent. So that's how we can get that alpha plus beta. And the I probably should have made more space for it. Let me make more space right now. The adjacent side to the sine of alpha plus beta, right? Or the adjacent side to the angle alpha plus beta is going to be 1 times the cosine of alpha plus beta, or just cosine alpha plus beta. And then the opposite of that angle is now going to be 1 times the sine of alpha plus beta. And then we just have this last triangle. And for this angle, we need to figure it out right here, this one. And one way of determining it is considering that if we have a triangle that is 90 degrees, with a 90-degree angle here and angle alpha here, then this last angle right here must be 90 degrees minus alpha, because the sum is 180 degrees. And then if we have some straight line, the interior angles will be 180 degrees. So if we know one is already 90 by construction and the other is 90 minus alpha, well then to get to 180, we need to have this be alpha. So that's that angle. And then similar to the last couple of sides, our hypotenuse is now sine of beta. So the adjacent side is going to be sine of beta multiplied by cosine of alpha. And the opposite side is now going to be sine of beta times sine of beta. Or alpha, I mean. So from here, since we constructed this to be a rectangle, we know that these lengths are equal side and these lengths are equal side. So these lengths are not the same to these. But okay, so from here, we can say that the sine of alpha plus beta is equal to the sine of beta multiplied by the cosine of alpha plus the cosine of beta times the sine of alpha, geometrically. And if we look, we see that we do have the same result. It's just not in the same order, but multiplication being commutative, we can change the order. And similar with addition, we can change the order to, say, sine of alpha times cosine of beta plus cosine of alpha times sine of beta to arrive at the same result. Now, for the other function, cosine of alpha plus beta, well, cosine of alpha plus beta plus sine of beta times sine of alpha is equal to the cosine of beta multiplied by the cosine of alpha. Isolating cosine of alpha plus beta by subtracting the other term leaves us the cosine of beta times cosine of alpha minus sine of beta times sine of alpha, which gives us our result. Again, multiplication is commutative, so we could change the order to further fit our formula that we originally had, so cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Now, from here, if we wanted to prove the difference, we need to recall that the cosine of a negative angle is going to just be the cosine of that positive angle, the result of that same angle but positive. That's because cosine's an even function. I'm going to leave that out for today. And for sine of a negative angle, it's going to be the negative result of sine evaluated at the positive of that angle. And that's because sine is an odd function. Again, similar to cosine, and I'm not going to prove why that is, because that's a little bit out of the scope of the video, but you could essentially derive your difference formulas by replacing beta with negative beta. And then, so for example, if I wanted to start sine, I'll show you how. So you would say sine of alpha minus negative beta, or sorry, plus negative beta. So then you'll have sine of negative beta times cosine of alpha plus, or sorry, I should use the formula in the textbook that's a little bit cleaner in order. So sine of alpha times cosine of negative beta plus cosine of alpha times sine of negative beta. And using the odd and even properties of sine and cosine, we can say that cosine of negative beta is just going to be equivalent to cosine of positive beta. And then sine of negative beta is going to be negative times sine, and then we can just, instead of writing cosine of alpha times negative sine beta, we could just say minus cosine of alpha times sine of beta. And as you could see from the difference, we have the same result. And we could just rewrite this as alpha minus beta. And you could do the same thing for cosine. I'll let you try to do that, right? So what is the cosine of alpha plus negative beta, right? That would be the cosine of alpha times the cosine of negative beta minus the sine of alpha times the sine of negative beta. So use the even and odd properties of sine and cosine to simplify your answer. Anyway, that's an alternative approach to proving these identities. These are very important identities, and the proof for them can sometimes be a little bit tricky. So I just wanted to give this alternative just in case you wanted to have a proof instead of just memorizing. As you use these more and more, you'll eventually just sort of have them memorized, but having a proof is always good to fall back on, especially if you haven't seen them in a while. Anyway, that was it.